Hi, everybody, and welcome to our second session in the Wildfires and Health series this afternoon. This session is going to be a series of lightning talks focused on measures and resilience in the context of wildfires and the mitigation of their health impacts. And we're super fortunate to have Dr. Colleen Reid moderating this session of lightning talks, as well as the next one. Dr. Reid is an associate professor of geography at the University of Colorado Boulder, and her research focuses on the health impacts of exposures influenced by global climatic changes and society's response to those changes. And she's led research projects on the health impacts of exposure to air pollution from wildfires, extreme heat events, and proximity to urban vegetation. Colleen, very happy to have you leading this session. I'm going to hand it over to you to introduce the session and the speakers. Thanks so much.
Thanks so much, Rachel. I'm very excited for all these lightning talks. This first lightning talk session is on measures and resilience. And the first speaker is Amanda Hoffman-Hall, an assistant professor of environmental studies at Eckert College. And the title of her talk is Intersecting Hazards, Wildfires, and Industrial Chemical Risk.
All right. Thank you so much, Colleen. Hi, good afternoon, everybody. Like you said, my name is Amanda Hoffman-Hall. I'm an assistant professor at Eckert College, which is a small liberal arts school in sunny St. Petersburg, Florida. And I study the intersection of environmental hazards, public health, and community resilience. My institution only offers undergraduate degrees, so I'm also extra proud to be sharing some of the work from my amazing undergraduate researchers today. Next slide, please. So like many of the talks likely will today, I'm going to start in California. In recent years, the fires across California have given us a really sobering reminder that when homes and human structures burn, the smoke is fundamentally different from what we see in a typical forest fire. Instead of mainly organic matter, we get a chemical cocktail of carcinogens, heavy metals like lead, and even asbestos released as buildings combust. We all know that wildfire smoke is harmful to human health already, but more and more we are seeing that as fire increasingly impacts human structures, it can be even more toxic. And so that leads to a bigger question for me. If residential structures can generate this level of hazardous pollution when they burn, we should probably worry about industrial structures as well. Next slide. So a recent study out of UC Berkeley found that wildfires increasingly threaten oil and gas fields, elevating the risk of releasing dangerous chemicals into surrounding communities. Under hotter, drier, more unpredictable conditions, these sites become not just economic risks, but public health hazards. So that research inspired my students and me to ask, what about some other industrial hazards that exist across the United States? And so we decided to dive into the EPA's toxic release inventory. The U.S. Environmental Protection Agency requires that all industrial and federal facilities that store and release hazardous chemicals report to the toxics release inventory. It's not a complete list of all dangerous facilities, but it is a pretty useful one. There's over 21,000 sites across the U.S., each handling chemicals linked to cancer, chronic conditions, acute toxicity, and serious ecological harm. So my lab's question is pretty simple. How many of these facilities sit in places where wildfire risk is growing the fastest? Next slide. So my student Ella Glass tackled this question for the state of Oregon. So using the TRI data set from the EPA and US Forest Service wildfire risk models, she identified 40 facilities across Oregon that are located in moderate to risk wildfire zones, moderate to high wildfire risk zones. These facilities, they store toxins, including lead, chromium, formaldehyde, and beyond. Any one of those chemicals can pose risks to nearby communities if they're liberated from the facility. So as one example, in its powdered form, chromium is extremely flammable on its own, and wildfires can transform chromium into its more hazardous carcinogenic form, hexavalent chromium. And we know that this isn't hypothetical, right? The research team that Dr. Mary Margaret Johnson presented in the earlier session detected elevated levels of hexavalent chromium in the air following the Eaton and Palisades fires. Next slide, please. And similar to this, during the 2018 Camp Fire, smoke containing elevated levels of lead traveled more than 150 miles away from the town of Paradise. So this emphasizes that these impacts can really be felt in areas even quite far away from the fires themselves. Next slide, please. And so building on this, my student Diana Price began mapping smoke plumes from wildfires, including this example from the Martin Fire, hypothesizing the distance of these impacts. Next slide, please. Meanwhile, another student of mine, Aubrey Inman, isolated TRI facilities that specifically handle lead in California. They then overlaid this with the Forest Service wildfire risk data and also census population information to estimate the number of people potentially exposed if a fire reached one of those sites. And Aubrey's findings I thought were pretty striking. Over 54,000 people live within 10 kilometers of a lead handling facility that's classified at high risk of being in a wildfire. Over 371,000 live within 10 kilometers of a moderate risk facility. So as more people continue to move into that wild and urban interface, and more industry also moves into that interface, impacts could be felt by more and more people. Next slide. And so to wrap up, I do want to share one compelling case study that my students Lucas Stubbins and Spencer Harris focused on. They analyzed TRI facilities nationwide to identify those with the highest potential hazard using the EPA's RSEI scores alongside wildfire risk models. So during their research, they identified the Freeport-McMoran mine in Arizona, which actually came alarmingly close to the Telegraph fire in 2021. So it was very close to being a disaster, but because this is about resiliency and I want to end on a positive note, this facility was actually very well prepared for this inevitability. Next slide. So the mine not only deployed firefighting resources to protect itself, they also provided support and resources to local fire crews, helping ultimately save 23 structures within the town of Miami, Arizona. So really, this case study was a reminder that preparedness matters, and that if we can partner between industry and communities, we can make a real difference in the future. Next slide, please. And so as these wildfire risks continue to increase, identifying these at-risk industrial facilities and then also supporting them and preparing for future fires will be essential to protecting public health. So my students' work shows that we can anticipate some of these risks, we can map them, and if we can understand them, hopefully we can prepare more before the next fire strikes. And so that's really been the goal of all the work that I've been doing with my students, to try and turn some of these hazards into foresight, and then foresight ultimately into resilience. So thank you so much for listening today, and thank you for having me.
Thank you so much. I just want to remind the audience that if you have questions for any of our speakers, please put them in the Q&A that you have in the portal today. And so I don't see any questions yet. So I'm going to start with one. So this is super interesting work, and I agree with you. Very exciting that you have undergraduate students doing such excellent research. I was wondering if you could share a little bit about the next steps on this in terms of for some of these. You talked about the resilience in the Arizona case, but are there any examples of other things that you found where facilities did burn, and were there any is there any follow-up that's going to happen there?
Yeah, that's a great question. So thankfully, well, I don't know if thankfully is the right word, but most of the evidence that we have of TRI facilities undergoing fire is usually accidental fires. So actual fires that are from accidents at the facilities themselves. We saw one recently in Conyers, Georgia, that impacted the metro area of Atlanta, but that was a fire that started within the plant. So we see these issues, knock on wood, we haven't seen a large TRI facility burn in a wildfire yet. I am hopeful that we are still far away from that, but I think that particularly the case with the mine does show that they are getting closer and closer to these types of facilities, and we've certainly seen TRI facilities be impacted by other disasters such as hurricanes, severe storms, things like that. So I think as we live in an increasingly chaotic climate world, we're going to start thinking about these things more broadly. So that's sort of the next steps for my lab, is sort of moving forward and trying to identify more across the entire US. Where are these most at-risk ones, and see kind of what plans they might be preparing for, or if they're not yet, maybe getting in touch with them and helping them with that. Thank you.
Yeah, great. Thank you. And I just want to check before we go to our next speaker, do we have time for one more question, and or is our second speaker here? Excellent. Okay, so our next speaker is Mercedes Bravo, and the title of their talk is No One is Immune, Neighborhood Trends and Disparities in Air Pollution Exposure in Chicago During the Summer 2023 Wildfires.
Thanks for the intro. So yeah, my name is Mercedes Bravo. I'm an assistant professor at Duke University in the Global Health Institute. And I did this work in collaboration with colleagues at the University of Illinois, Chicago at the Center for Climate and Health Excellence, CCHE, and the Children's Environmental Health Initiative, CHI. Next. So wildfire smoke is often concentrated in areas proximate to wildfires, right? We all know this, but the plumes can be transported over long distances, affecting communities far from the source wildfire. And that effectively happened in summer 2023, when smoke from fires in Canada was transported across large swaths of the US, including major American cities. Next. So there's already a large literature on how communities of color and lower SES experience disproportionate exposure to many environmental hazards, air pollution included. And so the idea here was to assess how wildfire smoke-related particulate matter, PM2.5, differed across regions of Chicago, and to understand if the patterns of disproportionate exposure observed elsewhere and sort of in normal times were also kind of reproduced here during a high pollution event. Next. So we use standard demographic data from the American Community Survey. Health data from the Chicago Health Atlas includes things like percent uninsured, hypertension prevalence, life expectancy, et cetera. We have hourly PM2.5 concentrations that were modeled on a 500 meter by 500 meter grid from May 1st to 2023, from May 1st, 2023 to July 31st, 2023. And this was actually done across Illinois, although this study is just in Chicago. And I point you towards this paper by Hong-Yup Kim and Chris Lim. And their generous data sharing is what made this study possible. And then we fit an interrupted time series model because we aren't necessarily expecting linear or monotonic sort of trends in PM2.5. Next. Great, thank you. So this is a graph of PM2.5 concentrations beginning in May 1st, ending at the end of July. The average pre-peak concentration, which is the sort of area to the left of that red dashed line. The red dashed line marks the first day of the peak period, which was a 2-day period. That pre-peak PM2.5 concentration was 14.5 micrograms per meter cubed. That's across the city. The peak concentration on day one was almost 100 micrograms per meter cubed, 99.7 micrograms per meter cubed. And post-peak concentration was 16.6 micrograms per meter cubed across the city. And this green dashed line represents US EPA NAAQS, a 24-hour standard, and the blue dashed line represents the PM2.5 concentration on non-peak wildfire smoke days, so sort of as a reference, kind of what an average concentration in Chicago might look like. Next. So just to illustrate some of, just to illustrate some of the demographic differences between regions, and I want to be clear that there is absolutely within region variability, but there are also regional trends, both in demographic and health, as well as in air pollution, which I'll talk about in a moment. So on the south side of Chicago, you have about 32% of the population that has a college degree. Over a third have hypertension, and life expectancy is 73 years. With the southwest side, the population, 13% have a college degree, a third has hypertension, and life expectancy of around 78 years. Contrast this with the north side, where the majority, 80% of the population has a college degree. Only a quarter of the population has hypertension, and life expectancy is 83 years, 10 years longer than South Side life expectancy. Next slide. So here you see air pollution levels across the study period. The peak levels were so high that we cannot put these on the same scale as the pre-peak and post-peak. But pre-peak, these highest concentrations are in yellow. You see it predominantly in southern regions of Chicago. But one thing I want to point out is that post-peak, the concentrations are elevated almost everywhere compared to pre-peak. So there was not really a return to a pre-peak baseline. There was a return to sort of a new normal, right? Next. Okay, and this slide has a lot going on, and I'm going to add another graph to it in a moment. But so here on the left, we show the smooth differences in daily PM 2.5 concentrations between each region compared to the southwest side. Chose the southwest side, that's analyst choice, right? We could have chosen another region to compare to. So if you look at the blue arrow pointing to that purple shaded line, that shows how pre-peak concentrations in the southwest side compared to those in the north side, right? Because we're looking at the graph of the north side. If you look at the blue arrow pointing to the green shaded area, you see that, you know, in the 10 to 14 days following those peak days, the concentrations are significantly lower on the north side compared to the southwest side. And then they sort of bounce back. Now, what is not obvious from this plot is what you saw earlier on the map, which is that the PM 2.5 in the post-peak period is elevated compared to the pre-peak period. This graph would sort of lead you to believe that perhaps they are the same. They're not. We are comparing differences between neighborhoods here. And then next, although I want to stay on the slide. Yes, thank you. So here we go to, if you see the blue arrow on the right, that's just the difference between the north region and the southwest on one of the, I think the first pre-peak day. So you can see here the north side had somewhat higher PM 2.5 levels, maybe around 2 micrograms per meter cubed higher, which I would argue is a substantial difference in normal times. And it is also not a large percentage difference given the overall levels of PM 2.5 ranging from 80 to 115 micrograms per meter cubed across the city. So percentage-wise, it's not large. All right, next. So just in summary, the PM 2.5 concentrations in the southwest side and far southwest side and other southern regions of the city were higher at baseline and also slower to decline following the peak wildfire smoke period. These are the same communities that typically experience higher air pollution levels, have a higher proportion Hispanic and non-Hispanic Black residents, higher prevalence of chronic disease, lower life expectancy. And I just think this long-range transport of wildfire smoke really highlights the need for studies to assess health risks of wildfire smoke, even in areas historically far from fires, and also consider and develop health protective measures for densely populated urban areas, again, both in locations at risk from wildfires as well as regions with historically lower risk, like Chicago. And next. And that's all for me. Thank you. Just a big thanks to collaborators on this paper too.
Thank you so much. Just a reminder to those in the session that you can put your questions in the Q&A. I also see a lot of questions for the first speaker that are happening offline after the talk. So if you miss a chance for a question to a speaker, you can do that. So just one quick question. You said a new normal. How long did that new normal pattern that you showed spatially last? Did it eventually go back to the old normal spatial patterning after a while, or do you still see this new spatial pattern of air pollution in Chicago?
Yeah, I would say that and I'm trying to think back since we ended up cutting this off in July, which was, you know, just an analyst choice, but the air pollution data does extend past July. I think some of the patterns, like the sort of baseline patterns, returned to normal, but there were elevations in air pollution sort of through August, you know, and you would also see, I don't know if you remember from the graph I showed with the daily pollution levels, where there were some days with very high levels, you know, around 50 micrograms per meter cubed. There were days in August that also approached, you know, 40, 50 micrograms per meter cubed, which you really don't see any of those in that pre-peak period. Yeah.
Great.
Thank you.
And because of time, we are going to move on to our next speaker. So our next speaker is Dr. Jo Cade Ghosh, and the title of their talk is, Did the Air Quality Index Accurately Convey Toxic Metal Exposures in the Eaton Fire Smoke?
Great. Thank you so much for the intro. I'm really pleased to be here to share this very brief analysis that I did looking at AQI and toxic metal exposures. Next slide. Great, thank you. So the Eaton fire, as perhaps many of you guys may remember, was a massive urban interface fire that happened in the Los Angeles area in January of this year. It ignited on the evening of January 7th, had a tremendous smoke production in the first few days, ultimately burned, thousands of structures, including many homes, businesses, and, as you can see in the photos, and churches. And burned and smoldered for several weeks after that, with the first significant rainfall occurring on January 25th. Because of the nature of this fire and the tremendous smoke production, there were a lot of community concerns about air quality and about specific questions about what the AQI does or does not tell you about what's in the air. Next slide. Okay, here's a map of where the Eaton fire occurred. And about 15 miles downwind, this is the air pollution monitor, whose data I used for this analysis. It's located in a community called Huntington Park. It's probably about southeast of the Eaton fire. And I do want to mention, in the first several days of the fire, we had predominantly Santa Ana wind conditions. So basically, this is an air monitor that could certainly be pretty effective in capturing those emissions when the wind direction is in the Santa Ana wind direction. I also do want to mention that this air pollution monitor was not a regulatory monitor, but instead it was a research grade monitor that was set up in that community. Next slide. Okay. So one of the reasons why I wanted to use this particular monitor was because it was already in place prior to the fire igniting. So that way we have several weeks before the fire where we can essentially create like a baseline of data. So I'm defining the weeks before the fire as December 15th through January 6th, and the typical levels as being between the 5th and 95th percentile during that time period. As soon as the fire starts, you can see that there was a very large peak in PM 2.5, been very high levels of PM 2.5 in the first several days. And then, the monitor continues to conduct measurements in the later fire period. One click, thank you. And so if we convert these PM 2.5 levels into a nowcast AQI, you can see certainly during the first 4 days of the fire, you have a number of hours where you are in the unhealthy to hazardous AQI range, but both prior to the fire and in the days after, you can see that there are also a number of hours that reach the unhealthy for sensitive groups, the orange band that is in the AQI, that particular AQI level. And so that's going to be the focus of this analysis. Next slide. Okay. So now turning our attention to the toxic metal pollutants that were measured at this particular air monitor. This air monitor actually measured more metals than this, but I chose these four because they are known toxic air contaminants, also known associated with fire emissions, wildfire emissions, and urban fire emissions in general. So that's arsenic, lead, copper, and manganese. So again, the nice thing about this particular data set is that you do have data from before the fire period, so you can look at some typical levels. Also knowing that during this time period, you have, Christmas Eve and New Year's Day, where you have, usually more, residential wood smoke burning and firework emissions that are also in the mix here. But definitely we see a very clear peak, particularly for arsenic, lead, and manganese. When the fire starts, copper, the peak comes a little bit later. The fire-related peak comes a little bit later, but you can see the kind of distinct patterns in these toxic metal levels. Okay, so moving on, we're looking at sensitivity and specificity for AQI at unhealthy for sensitive group levels. When the metal levels are high. And so in the weeks before the fire, again, AQI is not designed to be, to measure toxic metals specifically. And so you can see the sensitivity is pretty low, but specificity is relatively high. Next one. But during the first 4 days of the fire, you can see that the sensitivity increases by quite a lot. Specificity still remains high other than copper, which is moderate. And one more click. And then finally, during the later fire period, sensitivity drops drops back down and specificity remains high. And so one click. In other words, basically these first 4 days of the fire where you had probably the most smoke production, you can see there is a very distinct pattern that is different from the other two time periods where you have this high sensitivity, meaning that when toxic metal levels were high, AQI was typically unhealthy for sensitive groups or worse. Next slide. Okay, so key findings. Again, AQI was a pretty good indicator during those first 4 days of the fire, but certainly was not able to identify high metal levels in the later fire period. A few limitations I did want to note. Again, remember this was not necessarily the intention of AQI, but trying to use this pretty well-established metric, and one that I think people who've lived through many wildfires are pretty familiar with, to see how well it performed, as an indicator of metal air toxics. And again, I did want to mention that, of course, there are a number of things that AQI does not capture, ash or very localized exposures and so on. Next slide. Okay, just a quick list of data sources and a way to contact me. And that's all. Happy to take any questions.
And again, I don't yet see any questions in the Q&A. I think it takes a few moments, so please check that in a moment. I have a quick question. Was this metals in the particulate matter on a filter? And so you were actually looking at the metals in the particulate matter? Or was it measuring other metals some other way? Just was wondering if you mentioned that. I missed that.
I don't remember if this was a filter-based sample. I'd be surprised because it's a real-time instrument. I'd be surprised if it was, that method.
It's a real-time measurement of metals in the particulate matter. And so in terms of it's not relating all the time well with AQI, what would you say would be a good way to warn the public about when there are metals in the air, given that only during some periods it was aligned, and in some periods it was not aligned with the AQI?
Right. So, I mean, I think, for me, having previously worked in the regulatory sector and being the health effects officer for my local air district, this was always a challenge in communication, right? And so basically, issuing air quality alerts that are distinct from an AQI measure, but preferably wrapped into the same smartphone app, I think would be probably the most effective way to do that. And that's one of the things that, my team and I had worked on during my time there.
Excellent, thank you. All right, and our next speaker is Sienna from Northeastern University, and the title of their talk is Resilience Under Fire, Evaluating Behavioral Health Support for Wildland Firefighters.
Thank you. Hi, everyone. My name is Sienna. I am a fourth-year PhD candidate at Northeastern University in the Department of Public Health. That is wrong. I am in the Department of Political Science. I am focusing my dissertation work in part on investigating the persisting mental health concerns among federal wildland firefighters, despite increasing awareness and support through employee-sponsored mental health support programs. Go to the next slide. So this is a topic that is gaining traction both in government and media for a reason. You can see that some of the statistics that I've noted on this slide here, wildland firefighters self-report significantly high rates of depression, anxiety, PTSD, suicidal ideation, and substance abuse. And so this is an area that is both really interesting to me academically, but also very interesting to me personally. I was actually born and raised in a region of the country that is of particularly high risk for wildfires. And so I grew up seeing the impacts of fire on mental health up close and personally. You can go to the next slide. So part of the reason that I shared my background with fire is because that actually ended up being a key component in my success of this project. If any of you have ever worked with wildland firefighters before, you know that they are a very close-knit and closed-off community that is often very distrustful of outsiders, which is a point I will return to in a little bit. But being able to show up as a culturally competent party was key to getting my foot in the door. And the fact that I was able to conduct 39 interviews across all geographic regions in just 3 months, I think is a testament to just how much this community wants to be heard and supported. And so I want to note, you can see on the graph there on the right, I did choose to adopt a broad definition of fire because oftentimes studies focus only on operational firefighters, but their success and support for their mental health is very entwined and dependent on the wider fire community. And those individuals in that wider fire community are themselves often impacted. And so the yellow bar that I have there for militia refers to fuels technicians, people who work in dispatch, ecologists, biologists, other federal fire employees. I also want to note that I did apply for and received approval through the Wildland Firefighter Medical and Public Health Advisory Team. So I chose to do that as an added protection for the participants because they are undergoing a lot of uncertainty in their jobs right now. Go to the next slide. So I am still in the early stages of analyzing this research, but I wanted to share some of my initial findings with you, highlighted by a few especially poignant quotes. And so this first quote comes from a 20-year administrator who says that, yes, mental health supports are sufficient. For what we know right now, I think our agency is putting as much money and resources into it as the data shows we need. And that's really promising until you then compare it to this next quote that comes from a mid-career operational firefighter who says that they went to an outside party to talk to someone because they were worried that using agency resources would have negative repercussions on their jobs. Another common finding, a theme that I saw throughout my interviews, was the impact that having their basic needs met impacts mental health. And so this also comes from an operational firefighter who notes that one season, 60% of their crews were living out of their cars in the parking lot because they don't have access to affordable or sustainable housing. And then the final thing the final finding I wanted to note is that many people indicated that their mental health concerns come from safety risks, not from the fire itself, but rather from the impact from the public. And so this quote here comes from a firefighter who was responding to the Calf Canyon fire, which was a prescribed fire that reignited and burned several hundred thousands of acres. And this is a finding, this fear of repercussions from the public, from the community, was found both across operational fire as well as safety officers and communication militia members. I can move on to the next slide. So I just want to wrap up by noting that I think this is a really important time for research and change in this area. The Forest Service, the Department of Interior, federal fire in general is experiencing a lot of turnover. There's a significant loss of institutional knowledge, and combined with the demands for longer and more complicated fire seasons, it is ripe for change and policy implications. And then you're also seeing a massive culture shift among younger people who are more open about talking about mental health, as well as a increasing number of programs and implementations that are starting from the bottom up.
Great. I do have a question in the Q&A from someone. It says, regarding the behavioral health of firefighters, is this getting worse or better? And does health decrease over time? Are firefighters dropping out, not working fires because of behavioral health?
A lot of it is because of behavioral health. That's a great question. I don't know if we have good enough information to be able to really show how mental health has changed over time, because historically this has kind of been an understudied area. There's a lot of anecdotal evidence of this, but many times people, and a couple of the people I interviewed also noted that the reason they were leaving fire was because of the mental health impacts. And some of that does come from they have massive health exposure for their physical health as well as their smoke health. And I think you can see there's a bipartisan bill that was just introduced earlier this week to focus on smoke exposure for wildland firefighters. But it's all of these pieces of their job that then impacts their mental health. That's causing people to leave. There's also, I think, just generally in the federal government right now, a lot of uncertainty.
Okay.
And you're seeing fewer and fewer people moving from primary fire up into these admin and leadership roles, which is showing kind of this loss of knowledge.
Great. I'm sorry, I do have to cut off because we need to get to the next speaker, but hopefully we can continue all of this in the Q&A. Our next speaker is Claire Bekker, and the title of their flash talk is Comparing Air Quality Impacts of Land Management Scenarios to Mitigate Future Wildfire Activity in California.
Thank you so much. Hello, I'm Claire Bekker. I'm a PhD candidate at the University of California, Los Angeles in the Department of Environmental Health Sciences. Next slide, please. So as we know, wildfire burned area and severity have increased in California, resulting in greater exposure to harmful pollutants, such as fine particulate matter, PM 2.5. But studies have found that forests treated with fuel reduction, such as prescribed burning, can significantly reduce post-wildfire burn severity compared to untreated forests, as shown in this picture. Next slide, please. So, in response, California has committed to scaling up land management to treat 1 million acres of state and federal land annually. This figure from the California Wildfire and Forest Resilience Task Force shows California's progress in 2023 towards this goal, with almost 700,000 acres treated across the state. With the increase in fuel treatments, the location of these treatments will be critical in determining downwind air quality across the state, but there are different ways to prioritize treatment locations. Next, please. So our research question is making treatment allocations based on different priorities. How much and where are wildfire emissions reduced? And how do these changes affect community smoke exposure? Thanks. All right, so for the 2020 wildfire season, it was the largest in California history. And wildfires burned 4 million acres, providing more potential locations for reburning. So we looked at this hypothetical question of what would have happened if 1 million acres of burnt area had also been treated with fuel treatment reductions before the 2020 wildfire season. So first, we selected 1 million acres from fire perimeters based on 3 different priorities. One was restoring ecosystems for ecologically beneficial fire. The second was state plans from the California Resources Board. And the third was minimizing smoke exposure. And alternatively, we looked at what would have happened if all 4 million acres had been treated. Then for these selected fires, we converted high and moderate burn severity to low severity and recalculated emissions to simulate treatment. And finally, we're applying the original and modified emissions to atmospheric modeling to calculate changes in air pollutant concentrations. Next, please. So for our data sources, we used burn perimeters from the monitoring trends in burn severity. And then for emissions, we used the wildfire burn severity and emissions inventory, which is unique in that it calculates fire emissions based on burn severity classifications, which are shown here. And we leveraged this feature to calculate changes in emissions for each scenario based on changes in burn severity. And finally, we're integrating air quality modeling with STILT to calculate changes in air pollutants for each scenario. Next, please. So yes, next here when we show the 2020 statewide wildfire PM 2.5 emissions for each scenario classified by the burn severity category. So the wildfires for these scenarios are the same size as the original fires. We're just changing the burn severity. And the restoring ecosystems and state plan scenarios reduced observed emissions by about 6%, whereas treating all 4 million acres would reduce emissions by 14.7%. Next, please. And then here we show the original 2020 emissions in California in the first panel, and which fires were selected for treatment under the priority scenarios in the next two, and all of the fires in the last one. So the restoring ecosystems and state plans treatments selected some, but not all of the same fires, which affects the spatial distribution of emissions reductions. Next, please. So our ongoing work will utilize STILT to link scenario-based emissions with changes in air quality. And here we applied STILT in Sacramento, San Francisco, and Los Angeles to illustrate where emissions have the greatest impact on downwind air pollutant concentrations. And we're using STILT to assess how treatment scenarios impact air quality at these receptors. Next, please. So finally, what we've found so far is that different fires are selected for treatment depending on the prioritization method. And assuming 1 million of the 4 million acres had lower burn severity, we found a 6% decrease in emissions. And then our ongoing work is focused on these highlighted sections of the diagram, modeling the PM2.5 concentrations and including the minimizing smoke exposure scenario. And so we aim to provide decision makers with crucial information about the air quality trade-offs of each approach. Thank you.
Thank you so much. There's already a great question in the chat, and I also have another question, but because of time and our other speaker is here, I would like to move to Dan Jaffe's talk, and I hope one of the moderators here can help me with, can we stay past the time a little bit? Okay, should I move on to the final speaker, or should we do the one question in the Q&A for Claire before we move on?
I'm on a really tight schedule.
Okay.
I have class in 25 minutes, so.
Okay, all right. So we're going to move on to Dan Jaffe, whose talk is titled Rapid Method to Quantify Daily Smoke PM 2.5 and Ozone. We will return to the question for Claire after that talk.
Okay, so you're going to control the slides. I'm not seeing them yet.
I'm not seeing them.
Oh.
Almost. We're almost there.
Well, let me say, I'm sorry I had a little technical difficulty figuring out how to get in, but we're here. So out west, we've been looking at smoke for a long time, and it's gotten kind of a national problem. And so we wanted to develop some tools for being able to identify smoke impacts, particularly starting out on ozone, but then also on PM 2.5. One couple articles in review, or in one published in JGR, well, two published in JGR on ozone, one on PM 2.5 impacts in GeoHealth in Review, and then a long-term analysis on the comparative health effects of PM and ozone, and that's still in work. Next slide, please. I'll try to be quick. And I really want to acknowledge Habam Lee, who's my postdoc here at UW, University of Washington. So quick summary of the methodology. We're using HMS satellite product and surface PM 2.5 to quantify the smoke contribution for every day at every US air quality monitor. And that gives us information for about 85% of the US population in all 50 states. And then we use a machine learning method to quantify the expected ozone on non-smoke days and look at the pattern on the smoke days. And this analysis covers 800 some odd monitors, ozone and PM monitors at 358 core-based statistical areas plus 74 counties, about 85% of the population. And we have 2008 to 2024 completed now for both PM and ozone. And this is a rapid method, and we can add this 2025 data. We're planning to add this in February. And we're also doing comparisons underway with more traditional chemical transport models, both with models from EPA and NOAA. And that turns out to be important because as a lot of this has regulatory implications, we'd like to be able to know how well different methods agree. So next slide. So here's kind of a quick summary of the PM results. On the left is the average PM 2.5 exposure across the US and for that 85% of the population. And what this is showing is the average PM 2.5 averaged over every single day in 2019 to 2024. And you notice some of the numbers out west in some of the areas of Northern California and Oregon, and even getting up into Washington and Idaho, we see on average 1 to 7 micrograms per cubic meter. Those 7s are in Northern California and 5s in Oregon. So these are tremendous exposures that we see, that we've seen over the last 6 years. Central US, we see on typical values between 1 and 2 microgram per cubic meter of smoke, and in the east about 0.5 to 1 microgram per cubic meter. Now, a lot of that exposure in the east and in the central occurred in 2023. And if you look at that right plot, you see sort of cumulative exposure of the population to smoke PM 2.5 by year. And you see that in 2023, we had over 100 million people that were exposed to 2 microgram per cubic meter of PM, and about 200 million that were exposed to 2 microgram per cubic meter. And that's because there was so much smoke pouring down from the Canadian wildfires that it impacted the much larger populations in the eastern and central United States. So yeah, we've been getting it a long time in the West, but it was 2023 was the big one that hit the central and the eastern United States. Now, the central and eastern United States get smoke every year. 2023 was the biggest one. Next slide. Next slide, please. Yeah, and so sort of a comparable picture for ozone. The left slide is showing the average ozone contribution for every day in the ozone season, again, averaged over 2019 to 2024. And you see values up to about a little over a ppb for some areas in like Montana, North Dakota, California. We're seeing on average about a 0.5 ppb. But again, this is for every single day in the ozone season for 2019 to 2024. On individual days, we can see a lot more, up to 20 or 30 ppb. And what's interesting is that smoke is identified on 19% of all of the days between April and October, but they make up a large fraction of the highest ozone days. So on warmer days during the middle of the summer, smoke is really pushing ozone levels up to higher levels. And on those 10 highest days, then we see numbers that are even about 10 ppb averaged over the 10 highest days at every monitor in each state. So the smoke impacts on the photochemically generated ozone are much stronger on photochemically active days. And it becomes both a health issue, but also a policy issue. Next slide. And there's a lot on this, but really the most important takeaway is how things have changed over the last couple of decades. And so this is looking at the PM and ozone, both in terms of the magnitudes, and that's on the right slide where we have microgram per cubic meter and ppb of smoke impacts, smoke ozone, averaged for the whole country, and the health effects in terms of ER visits. And so first point here is that the smoke impacts have clearly accelerated in the last 5 or 6 years, particularly starting in about 2020. And the second point is that the health effects based on our calculated risk functions are about double for PM 2.5 compared to ozone. So we think the PM 2.5 is a bigger health effect compared to the compared to the ozone impacts. And I think this may be my last slide. I can't remember if there's one more. And we've put all of these data on an app, and you can explore the data sets for all of the 400 some odd sites around the country. And what you're able to look at here is how much PM came from smoke for every day of the year and how much ozone we think came from the smoke as well. And it's kind of interesting to explore and look at different regions and look at impacts of big fires across different areas. So I'd encourage you to play with that and send us any feedback if you are interested. And I think that's my last slide, isn't it?
It is.
So that's it from me.
Thank you. Do you have time to stay on for any questions?
Yeah, for about 10 more minutes.
All right. Well, because I've noticed that it takes people a few moments to type in their questions, I think because there is a question for Claire, I'm going to move to the question for Claire, and then I'll see if one shows up for you, Dan. Claire, if you're available. The question in the Q&A is regarding air quality and the relationship between treatment and wildfire smoke exposure. Wouldn't fuel treatment as a result of prescribed fire just cause 2 smoke exposures in 2 different events? Even more, smoke from prescribed events seems to stick around due to weather and smoke sinking. What have you found or seen on this topic?
Yeah, absolutely. So we're trying to integrate that into this paper as well to account for the prescribed fire smoke. California plans to treat, of the 1 million acres, about 40% with prescribed fire. So, and the rest with like mechanical and thinning. So we're looking for ways to simulate the prescribed fire events as well, in addition to the reduced wildfire smoke. And that can give us a more like complete perspective on how both the prescribed fire and wildfire contribute together to smoke exposure. And like the question asked, there's likely to be more local impacts for prescribed fire, whereas greater downwind impacts, such as in major cities, for larger wildfires due to the hotter conditions causing greater injection heights into the atmosphere.
Excellent, thank you. And then there is a question that came in for Dan Jaffe. The question is, for wildfire-associated ozone, do you think the observed concentrations result primarily from local ozone formation near the fire and subsequent transport, or from the transport of ozone precursors that later react to form ozone downwind?
Yes, that's a great question. And we debate that question a lot. And I think it's both. Honestly, I think it's predominantly from the mixing of VOCs in the smoke plume with urban NOx. I think that's the dominant mechanism, but we also think peroxyacetyl nitrate, PAN, is probably also important. So that it's a complicated question, good question, but the answer is all of the above.
Excellent. Well, thank you to all of our presenters. I actually have more questions for many of you, and I'm sure many of the people attending the session do as well. This has meant a lot of interesting thoughts that I've got. And so I might be following up with some of you by email. But for now, because we are past time, I think we will end the session. And these were all excellent talks.